So let's talk about modeling with matrices. I know Lee is covering this. I don't know about the other two instructors. This is problem number 17 from section 8.5, in case you're curious. Suppose influenza viruses are plotted in two-dimensional space, and the X and Y coordinates change from year to year, according to the following diagram. It sounded like that was the end of a sentence, because that's certainly how I said it. According to this diagram. X, Y, and we have the following. So what does this even mean? Really good question, right? Like somebody's writing down something that feels like totally alien to me when I first saw it. So this is supposed to represent how things change from year to year. So in the beginning, we have some X and some T, some point X, Y in space. Sorry, I said T, I meant to say Y. Sorry about that. We have some X and some Y. So we start with some X and some Y, which we're going to write as a vector. And then in the next iteration, we're going to look at what's going into X and what's going into Y. So what's going into X? Well, X is going into itself times 2. So in the next iteration, this is going to be a better way to write this, but I'm kind of just showing you my thought process before we write it like the more official way. In the next iteration, we're going to get 2X plus 3Y in the X spot, because the stuff that's going into X is 2 times X and 3 times Y. And the stuff that's going into Y is going to be no X, because there isn't an arrow from X to Y. But we already do have 0.9 times Y itself. So that's what I'm thinking of as my next iteration. Now, the way we write this as a set of difference equations, which I've never loved that term. Difference equation just means like kind of what do you have next after you in the next iteration. That's kind of how I think of it. This is we're getting at the thing you'd ask, among other people that you had asked about. Cool. So the difference equations are just saying, how much do I have in the next year based on what I had in the previous year? So what is X in the next year, in year T plus 1? Well, it's 2 times the X that was in the previous year. So it's 2 times X sub T plus 3 times the Y that was in the previous year. 3 times Y sub T. So based on whatever you had in the previous year for X and Y, this is what you're going to have for X in the next year. And similarly for Y in the next year is going to be 0 times the amount of X we had in the previous year, plus 0.9 times the amount of Y we had in the previous year. So that's how you can take a diagram like this and make it into some difference equations. But what I really want you to see is that these difference equations are just matrix multiplication, which is why we're talking about it, right? It's because it's going to be matrices. This really can be rewritten as the next year matrix X sub T plus 1, vector matrix. We kind of throw those words around interchangeably. X sub T plus 1, Y sub T plus 1. And it's going to equal a 2 by 2 matrix, which is the coefficient matrix, so-called because it is literally the coefficients of X and Y, 2, 3, 0, and 0.9. Times the variable matrix vector xt y sub t. Check it out, right? If I do the multiplication here, row 1 dotted with column 1 is 2 times xt plus 3 times yt. And row 2 dotted with column 1 is 0 times xt plus 0.9 times yt, which is exactly what we have over here. So these are the same. You should, at this point, if you are not already, you definitely should spend some time practicing making sure you're comfortable with the matrix multiplication. Because people are just going, your teachers are going to assume you know how to do it rapidly. So, in fact, yeah, that's all we're going to do with that problem, really. So let's take a break here for just a second. Everybody multiply these matrices together real quick. Multiply those together as fast as you can without showing as little work as possible. And then I'll give you another one too. There's a second one on there as well. Give you 10 more seconds. All right, that's kind of a long 10 seconds. All right, so here's how I would look at it if it were me trying to do it as fast as possible. First row with first column. So what I'm really doing is I'm thinking, I'm pointing at 2 times 5 plus 1 times 1. But I'm not saying 2 times 5 in my head. I'm saying 10 plus 1 is 11. And then 0 plus 6 is 6. And then 15 plus 4 is 19. And then 0 plus 24 is 24. You can show more work, it's totally fine, but you want to be comfortable with this so that you can do it relatively quickly and not be like, how am I multiplying these together? Oh yeah, it's always rows of the first matrix dotted with columns of the second matrix. Same deal down here. Row 1 with column 1 is going to give me 12 plus 4 plus minus 2. So 12 plus 4 is 16, minus 2 is 14. And then 6 plus 0 plus 10. Is that the right size? Let's see. That's a 2 by 3. That's a 3 by 1. The inner dimensions match. The outer dimensions are 2 by 1, which this is a 2 by 1. Good to go. Cool. Questions about that? Right. Back to modeling with matrices. Together here. Let's look at another example from section 8.5. We'll do a few of these and then we'll move on to more just matrix stuff. So 8.5, number 21. This one kind of requires a lot of writing. I'm going to try and make it as painless as possible, but there's a lot of words right here. So here's the setup. Suppose that one of 3 different alleles. Could I tell you what an allele is? No. Could you tell me what it is? Maybe. I don't know. You don't have to. I'm not asking you to tell me, but like I'm like, I think it's something with genetics. I really have no clue. It doesn't matter. We're doing the math, not the biology. Suppose one of 3 different alleles is present in each individual in a population. In each generation, 5% of individuals carrying allele X mutate to carry allele Y. And then 3% of those with X mutate to carry Z. And the rest of the X's, the other 92%, remain unchanged or unmutated. I think that sounds better. And then similarly, we'll say 0.1% of this is why this takes so long to write. There's all these things to write. 0.1% of individuals carrying Y mutate to carry Z. And the rest remain unchanged. So many words. Finally, 90% of those carrying Z mutate to carrying X. And the rest unchanged. Goodness. Let's draw a diagram before we write out the matrix to visualize this. There's a better word there. Let's not actually do that. I want to do that. Yeah, sure. So I'm going to draw a diagram because I like the diagrams. The diagrams I think are fun to draw. You can draw some circles, you can draw some arrows. Okay. So X's mutate into Y's and Z's. So how much of X mutates to become Y? I don't remember. What was it? Was it 3% or was it 5%? 5. But we don't want to write percentages, we want to write decimals. So instead of 5%, we should write 0.05. And what percent of X is mutate to Z is 3% or 0.03. And then, let's see, cool. And then the rest remain unmutated. Okay. Which I think means we should also have an arrow going back on itself saying the other 92% stick around and stay X's from one generation to the next. And then 0.1% of the Y of the individuals carrying, I forgot to write the Y there. I know I forgot to say. 0.1% of individuals carrying Y mutate to carry Z. So 0.1% is 0.001. So from Y to Z, 0.001. And the rest remain unmutated. So the other 99.9% stay as Y's. Finally, 90% of Z's mutate to carry X. So we have 90% of Z's, which is 0.9, mutate to carry X, and then the other 10% of Z's stay as Z's. I don't know why I wrote a 0 there, but I did. I could write a 0 there too, I guess, but it's not necessary. So there's our diagram. I like the diagram. I feel like the diagram is kind of useful. But you don't have to like the diagram. Let's write out our difference equations from one generation to the next. So typically we're going to go in alphabetical order. So x sub t plus 1. So you're always trying to figure out what's going into your x to figure out what the next one is. So what's going into x? Z is going into x and x is going into x, but y is not. We want to try and keep the order consistent. So I'm going to write x, y, z. So I'm going to say that what's going into x sub t plus 1 is 0.92 times x sub t plus 0 times y sub t plus 0.9 times z sub t. I couldn't tell you why I decided to write a 0 in front of my decimal sometimes, not other times. There's no rhyme or reason. I just feel like doing it sometimes. So there's no reason I wrote a 0 there and I didn't write one there other than just I didn't do it. So for y sub t plus 1, let's see. So what's going into y? Well, 0.05 times x sub t plus 0.999 times y sub t. And that's it. That's all that's going into y. So 0 z sub t, if you like. Finally, what's going into z? Well, let's see. We have 0.03 times x plus how much y? 0.001 times y sub t. Finally, how much z? 0.10. Or just 0.1. That is our system of difference equations, which again is kind of a pain to write out. We would much rather write it as a matrix. So we can write the 3 by 3 matrix of coefficients. I'm going to write that first, but I'm going to fill in something on the left and on the right. So the matrix of coefficients is just, by the way, this is why the writing things in the same order is important. So that you can write the coefficients in all the right spaces. So 0.92, 0, 0.9, and then 0.05, 0.999, 0, and then 0.03, 0.001, and 0.01. 0.1. Ah, almost made it. That's your coefficient matrix. And if you multiply that matrix by what happened this year, x sub t, y sub t, z sub t, you're going to get what happened or what happens in the next year. X sub t plus 1, y sub t plus 1, z sub t plus 1. And let's think about it for just a second. If you actually think about doing the multiplication, this row with this column gives you exactly 0.92 times x sub t plus 0 times y sub t plus 0.9 times z sub t, which is exactly the equation we have there. And so on and so on. I don't feel like I need to say the other ones. Questions about what we've done here? Yeah, I think that's a good start for that. We'll come back to that if needed. So does that kind of clarify what's going on? Good. It's going to get a little more complicated, but we'll kind of leave that there for now. I think that's a good spot. If you're interested, if anyone's interested, I do have a handout right here that you're all welcome to grab a copy of as you exit that has more examples and more questions for you to work on here. And then I will post the solutions to it on Canvas so that you can work on it on your own and then look at the answers on later after you look at it. If your teacher decides to cover that. I don't know if let's call them Gold. I don't know if Gold or Alameda are covering that, but if they are, I encourage you to take a look at that and we'll talk more about it. All right, cool, right on. Let's grab this other stuff here. Back to talking about matrices. Yeah. All right. Sorry, 1 second. All over the place. Yes.
I don't know how to pronounce it.
Okay.
The values.
Eigenvalues. That is yes. I've been waiting to get to eigenvalues. There's been like so much. Yes, eigenvalues are where we want to be. We're almost there. Yes, eigenvalues and eigenvectors as well. Let's see, we did that last time. Cool. Yeah, all right. So a couple reminders from last time. Just because the things I'm going to remind you of are things we're going to need. So reminders. For a general matrix A, a 2 by 2 matrix A, which I'm going to usually label as A, B, C, D, unless I have another reason to do so. 3 things. The A transpose is just equal to rows becomes columns, columns become rows. So it's going to be, the first row is going to be AC, the second row is going to be B. The determinant of A, which is sometimes written like an absolute value. So you might see your teacher write it like this. It's atypical in this class, but not impossible. Is just the product. So I'm always going to say it this way, and you should get used to thinking of it this way. The product of the diagonals minus the product of the off diagonals. That is not true for larger square matrices. It is true for 2x2 matrices. Has anyone talked about determinants with 3x3 matrices? Good. If you do, let me. You have? Ah, darn. Okay. Well, we'll talk about that. We have time at the end of class today. We'll talk about that. It's still there's an easy way to do it for 3x3. For larger ones, it is harder, like exponentially harder, kind of. So that's your determinant. And then, thirdly, the inverse of A, if it exists, is equal to 1 divided by the determinant of A. So 1 divided by the product of the diagonals minus the product of the off diagonals times the matrix where you interchange the diagonal entries. So A and D switch spots, and the off diagonals change signs. So if it was positive, it's now negative. If it was negative, it's now positive. And what's kind of cool about this is you can totally check it. Let's check. If we multiply A inverse by A, well, let's actually do it. A inverse is 1 over AD minus BC, D negative B negative CA, times A, which is A, B, C, D. Ignore this constant out in front here for the moment. It's just going to stay. So that constant stays out in front. And now let's do the matrix multiplication. So D times A minus B times C. I'm going to write that as A times D minus B times C. So D times A is A times D, and plus negative B times C is minus B times C. All right, and then over here in the first row, second entry, first row, second column, D times B minus B times D is 0. But let's write it out anyway. We've got BD minus BD. Down here in the second row, first column, negative C times A plus A times C. Oh, that's also 0. And then finally over here, negative C times B plus A times D, or AD minus BC. So look what I've got. I've got 1 over AD minus BC times AD minus BC, 0, 0, AD minus BC. But 1 over AD minus BC times AD minus BC is what? Everybody, show me on your fingers. How much is it? Yeah, it's that many. It's that many. It's 1. So that times that is 1, 0, 0, and that times that is 1. Which is what you should get when you multiply two matrices together that are inverses. You should always get the identity matrix when you multiply them together. So A has an inverse, or A is invertible, as long as the determinant of A does not equal 0. Right? Because if the determinant of A is equal to 0, then we have division by 0 here, and that wouldn't work out. But as long as the determinant is not equal to 0, it is automatically guaranteed that A has an inverse. And that's true for larger matrices as well. Okay. Cool. Yeah. We'll come back to that. Yeah. Let's try it. Yeah, yeah, that's fine. It's all good and well. Yeah, all right, we'll do that. You will come back to it. So we got enough time. Yeah, I need to build up just a tiny bit, but we're gonna get there, I promise. So what happens when we multiply a 2x2 matrix by a 2x1 vector? For example, the matrix 1, 3, 2, -1 times the vector 1, 2. Well, graphically, here's what's happening. Taking your vector 1, 2, and you're changing it. I call that vector V for a second. When I do this multiplication, you also do the multiplication real quick. See what you get. I'm going to call it W. Let's see, 1 plus 6 is 7. 2 plus 0 is 0. Or sorry, 2 plus negative 2 is 0. So my vector, my resulting vector is the vector 7, 0. So when you multiply a matrix by a vector, you get a new vector. And I'll point out that multiplying, gosh, can I spell? No. Multiplying V by A did two things. Changed both the direction of the vector and the length of the vector. Length, a better word, a more mathy word for length is going to be magnitude. But they mean the same thing. They just mean how long is the vector. Okay. That doesn't always happen. There are some special matrices we can multiply by that don't change the length or that don't change the direction. Let me show you one just because I think it's super cool. So this matrix, the rotation matrix, rotation, yeah, I can spell. Yep. The rotation matrix R theta is equal to this 2 by 2 matrix. It is cosine of an angle theta, negative sine of the same angle, sine of the same angle, cosine of the same angle. This matrix rotates a vector counterclockwise by the angle theta. And it doesn't change how long it is. It preserves the length or the magnitude. Kind of neat. Let me show you an easy example. Well, an easy example if you remember your trigonometry. So let's say our angle was pi over 3. So for theta equals pi over 3, r sub pi over 3 is going to be the matrix cosine pi over 3, negative sine pi over 3, sine pi over 3, cosine pi over 3, which is equal to, let's see, cosine of pi over 3 is 1/2. Sine of pi over 3 is root 3 over 2. So we get a negative root 3 over 2. And then we get a root 3 over 2 and a 1/2. Okay, so what this matrix should do is for any vector we start with, it should rotate it by 60 degrees or pi over 3 radians. Let's actually do that. Let's take a nice vector. Let's say our vector is the vector 2, 0. Yes, I've decided to use a different notation because I decided to. Not for any good reason other than I just wrote it that way, which people will do all the time. So if I do my rotation matrix times my vector, that's going to be 1/2 negative root 3 over 2, root 3 over 2, 1/2 multiplied by the vector 2, 0. Okay, let's see what we get. So 1/2 times 2 plus this times 0 is going to be just 1/2 times 2, which is 1. And positive root 3 over 2 times 2 is root 3. And 1/2 times 0 is 0. So root 3 plus 0 is root 3. Let's draw it. And let's call this resulting vector W. So here I'm going to try and draw this fairly well to scale so that we can see what's happening. So my initial vector V was the vector 2, 0. So over 2 and up 0. And then the resulting vector W is over 1 and up root 3, which is about 1.7. So there's my vector W. And it certainly looks like, yeah, we rotated that vector 60 degrees or pi over 3 radians. And we totally did. Kind of neat. Okay, that's not really the point. The point is just to point out that sometimes there are special matrices that preserve something. Some matrices preserve length, like the rotation matrix, right? This matrix, the length of W didn't change, right? If you found the have we talked about finding the magnitude of a vector? I know I've said this word like 3 times. Have we? If we haven't, that's okay. So let me just say real quick here. The magnitude of V, the way you find the length of a vector is you take the square root of the sum of the squares of the components. It's really just the Pythagorean theorem, right? You're just saying, oh yeah, I'm finding the length of the hypotenuse. That's going to be the square root of 4, which is 2. And notably, the magnitude of W, or the length of W, is the square root of 1 squared plus the square root of 3 squared, which is the square root of 1 plus 3, which is also 2. Oh, those vectors have the same length. They have the same magnitude. But really what we want to get at is the fact that, yes, there are some matrices that preserve the length and rotate the vector, that matrix. And there are some other special matrices that preserve the direction and change the length. And those are the vectors and matrices that we actually care about. So, come on. Sure. Yeah. So let's look at this matrix here. We're going to let A equal the matrix 3, 6, -1, -4. And the vector V is equal to -6, 1. And let's see what happens when we multiply A times V. So A multiplied by V, which is 3, 6, -1, -4, times -6, 1 is going to equal, let's see, 3, so -18 plus 6 is -12. And 6 plus -4 is 2. And now I want you to notice that this vector is a multiple of the original vector V. It is double V. This is equal to 2 times -6, 1, which is equal to 2 times the vector V. So here's what we have. We have the matrix A times V is equal to the scalar 2 times V. Here is some language for you. Yeah. So what I'll point out here is that V equal to -6, 1 is an eigenvector of A, associated to the eigenvalue lambda equal to 2. Lambda is the standard choice of variable name for eigenvalues. Get used to writing it. So whenever you take a matrix and multiply it by a vector and you get back a multiple of that vector is an eigenvector, and that multiple is the eigenvalue. Now, the real question at hand is, how do we find these things? Because I just gave you some stuff and you're like, well, let's see if it works. But I could have given you a matrix and a bunch of different vectors and have this not happen. So how do we find them? How do we find eigenvalues and eigenvectors? And we definitely do find them in that order. Well, let's start with the matrix A. So, oops, oh my gosh, pens. So here's what we want. We are looking for vectors V and eigenvalues lambda such that A times the eigenvector is equal to lambda times the eigenvector. And I would encourage you to think of it this way, although there are actually going to be two kind of different ways we talk about solving things in a second here. So we're going to rewrite this because that's not going to help us solve it. So here's how we're going to solve it. We're going to rewrite this as we're going to rewrite AV equal to lambda V as AV minus lambda times V equal to not the number 0, but the 0 vector. Because A times the vector is a vector, and lambda times the vector is a vector. And when you subtract two vectors, that are the same, you don't get the number 0, you get the vector 0, which consists of all zeros in whatever the correct size of vector would be. Okay. But I can't factor out a vector v here because if I did, I'd be left with a matrix minus a number. That's a problem. You can't do a matrix minus a number. They have to subtract matrices, they have to be the same size. So we're going to fix it. We're going to rewrite this as A times the vector v minus lambda times the identity matrix times the vector v. Because the identity matrix times v is still v. Right? I really want to make sure you guys are all super cool with this. That's why the identity matrix is super special. The identity matrix multiplied by any other matrix or vector will always give you back that matrix or vector. It's like the number 1. So this is just v. But now look what I can do. I can rewrite that as A minus lambda I times the vector v. A times v gives you A times v. And lambda I times v gives you lambda I times v, which is just lambda times v. All right, so we want to find solutions to this. And this is where I've maybe gotten ahead of myself. Yeah. Okay, I'm just looking at it. Yep. So let's back it up for a second. I need to say a couple things here before we can get to the result we want here. So what if I was trying to solve? Yeah, wow, my writing's really quick at there. If I want to solve a matrix A times a vector X equal to 0, there's a couple things that can happen. One thing that can happen is that X is just the 0 vector. For example, the following. 2, 3, 4, 5 times the vector X, which I'm going to call X1, X2, equal to 0, 0. The only way to solve this is for X1 and X2 to both be 0. There is no other solution. Why not? Good question. Well, the real reason why not is because this system of equations represents 2 lines. And these 2 lines only intersect at the origin at 0, 0. If I write this here, I should use X and Y, sorry. 2x1 plus 3x2 equal to 0, and 4x1 plus 5x2 equal to 0. This is a line that goes to the origin with a slope of negative something, negative 2/3. And this is a line that goes to the origin with a slope of negative 4/5. And those lines that have different slopes that go through the origin only intersect at the origin. So sometimes you solve this and your only solution is 0, 0, which is a bummer. Because 0, 0 is never going to be an eigenvector. I want you to take that to heart, especially for those of you going on to 17C. I want everyone to know 0, 0, or the 0 vector in general, never an eigenvector. Okay. The other thing that can happen is instead of having just one solution, you can have, sorry, yep. you can have infinite solutions. So let me show you what I mean. Maybe we have something that looks like 2, 3, 4, 6 times, I'll use xy this time instead of x1, x2 equal to 0, 0. Why does this have infinite solutions versus the other one having only one solution? Well, because both of my equations are really the same. This first equation is 2x plus 3y equal to 0. And the second equation is 4x plus 6y equal to 0. But those equations are the same line. They are both the line that has a slope of y of negative 2/3 or negative 4/6. So they're the same line, which means every point on this line is a solution. So my solutions are lots. Solutions are, let's write it this way. 0, 0, or x could be 3 and y could be negative 2, or x could be 6 and y could be negative 4, or x could be negative 3 and y could be positive 2. Literally, the list goes on forever and ever and ever and ever. Okay. So we are interested in finding solutions of this type, where there's an infinite number, because then the vector here isn't going to be the 0 vector. And that's what we actually care about. We care about this eigenvector can't be the 0 vector. So we want our matrix to be the kind of matrix that has an infinite number of solutions. Well, let me ask you all a quick question. For this matrix here, 2, 3, 4, 5, what's the determinant of that matrix? Everybody should do it in your head if you can. That minus that is, it's a negative number. It's negative how much? Negative 2, yes, 10 minus 12 is negative 2. Okay, and when your determinant was that, we got one solution. It was only 0, 0. Okay, for this matrix over here, what's the determinant of that matrix? I do want everyone to tell me right now what that determinant is. Yell it loudly. Well, come on. Please. Somebody say it. 2 times 6 minus 3 times 4. 0. When the determinant is 0 is when you get infinite solutions. Meaning you can have a vector here that isn't just the 0 vector. Okay, so here's what we need. We need, for this to be meaningful in any sort of way, shape, or form, we need the determinant of that matrix, A minus lambda I, to equal 0. And that's how we're going to find the eigenvalues. So let's do it. Let's look back at the matrix that we started with, which was, I forgot where you went there. The matrix was 3, 6, negative 1, negative 4. So for A equal to 3, 6, negative 1, negative 4, we're going to find the determinant of A minus lambda I. So A minus lambda I is going to be 3, 6, negative 1, negative 4, minus lambda times the 2 by 2 identity matrix, which is really just a lambda on the diagonals and zeros in the off diagonals. So here's what we're doing. We're taking the determinant of the matrix 3 minus lambda, 6 minus 0, negative 1 minus 0, and negative 4 minus lambda. Now, when you do this, because you'll do this a lot. When you do this, you're going to get used to being, oh, we're just going to subtract lambdas on the diagonals. You don't need to write out A minus lambda I is this minus that, which is equal to this. You're just going to say it's subtract a lambda there, subtract a lambda there, and then take the determinant. So the determinant is going to be 3 minus lambda times negative 4 minus lambda minus 6 times negative 1. And we're going to set that equal to 0. Okay, let's multiply it out. 3 times negative 4 is negative 12. 3 times negative lambda is minus 3 lambda. negative lambda times negative 4 is plus 4 lambda, minus lambda times minus lambda is plus lambda squared, and minus 6 times minus 1 is plus 6. Let's rewrite this so it looks like a quadratic that we're used to solving. Lambda squared, plus 4 lambda minus 3 lambda is plus lambda. Negative 12 plus 6 is minus 6. And if the person writing the problem is kind, this will factor. And this does factor as lambda plus 3 times lambda minus 2 equal to 0. So our eigenvalues are lambda equal to negative 3 and lambda equal to positive 2. And we already knew 2 was one of them because that was what we started with, was that lambda equal to 2 was an eigenvalue. We found that when we did the beginning of this section. Okay, so we have the eigenvalues. How do we find the associated eigenvectors? Well, for lambda equal to negative 3, we want to find the eigenvector v such that A times the eigenvector is equal to lambda times the eigenvector. Here's how I always think of it. We don't know what the vector v is. So when I write this equation, I'm going to write A 3, 6, negative 1, negative 4 times the unknown eigenvector. We're trying to find this. We don't know it. Equal to the eigenvalue, negative 3, times the same unknown eigenvector. Most of the time when you do this, you don't have to use both sets of equations. Here's what I mean. My first set of equations would be 3 times x plus 6 times y equal to negative 3 times x. Right? First row with first column equal to the first entry. And my second equation would be negative 1 times x minus 4 times y equal to negative 3 times y. But in almost every instance, there are some instances where one of the equations doesn't help you at all. But in almost every instance, these two equations yield the same results. Here's what I mean. If I isolate y, 6y equals negative 3 minus 3 is negative 6x. Divide both sides by 6 because I can. Y equals negative x. Or over here, solve for y. Negative 4y equals negative 3. That doesn't look right. Oh, no. I was about to do the wrong thing. I was about to add x's to y. This was a problem. Not that. Let's leave the x over here and say negative x equals negative 3y plus 4y is positive y. Or y equals negative x. We get the same relationship between x and y. Here is the part that throws people off. You have to make a choice. You have to pick a number for x or for y. Pick literally any number you want with one exception. You cannot make choices so that you get x equals 0 and y equals 0. You can get x equal to 0 and maybe y equal to 1. That happens sometimes. But here, we can't pick x equal to 0 because if x is 0, then y is going to equal negative 0, which is also 0. So what's any other number we could pick? 2. Great, perfect. If x equals 2, y equals negative 2, and my eigenvector, which is xy, is 2, negative 2. Now I will tell you the standard choice is to pick integers that are as small as possible. So if I was making the choice here, I would have picked the eigenvector to be 1, negative 1, or negative 1, 1. But any of these choices is correct. Because once you have an eigenvector, any multiple of it that is not the 0 vector is also an eigenvector. So there are literally an infinity of correct choices here. But the standard choice is this one or that one. But that's also correct. So is 6, negative 6. So is negative 7, 7. Any multiple is also a valid choice. I will point out, I want to say more, but so I'll just say one more quick thing. The other way of doing this, which I don't prefer, but the other way is instead of solving this, you solve a minus lambda I times v equal to 0. So I wrote it that way instead. I would do 3 minus negative 3, 6, negative 1, negative 4 minus negative 3 times xy equal to 0, 0. Check this out just for a second here. I'm going to simplify this. I've got 6, 6, -1, and -4 plus 3 is -1 times xy equal to 0, 0. And I think you can see how both of the equations I'm going to write down are going to be the same equation essentially. Either 6 times x plus 6 times y equal to 0, or -1 times x plus -1 times y equal to 0. Both of these still yield the same relationship, that y is equal to -x, or that x is equal to -y. And so again, if I pick x equal to 1, then I'm going to get y equal to -1. And so my eigenvector is going to be the same as it was up there. xy, which is my eigenvector, is going to be 1, -1. Both ways are fine. I prefer doing it this first way because I feel like this is more the essence of what it means to be an eigenvector. That when you multiply the matrix by the eigenvector, you get the eigenvalue times eigenvector. But a lot of teachers will do it this way because it feels, I don't know, because they like, I don't know why really. This sometimes I'll say, sometimes if your eigenvalues are gross, like if your eigenvalue is 4 plus the square root of 3, or imaginary, which it will definitely be next quarter, doing it this way leads to less computational complexity.